Today we're going to go over section 2.4 and 2.5. Section 2.4 is about the structure of the atom, and section 2.5 is about the electron arrangement in atoms. Over the past century, scientists have discovered that the atom is composed of three subatomic particles: the positive proton, the neutral neutron, and the negative electron. So what we know about the atom is that there are two main parts. The center of the atom is called the nucleus. The outside of the atom is called the electron cloud. Inside the nucleus, we have our positive protons and we have our neutral neutrons. And then in the electron cloud, we have our negative electrons. The symbol for the proton, when you see me write it in class, is the P positive. Easy to remember. P stands for proton. Positive is its charge. Its relative mass, we'll talk more about relative mass later, but its relative mass is 1 atomic mass unit, which is 1 AMU. The actual mass of a proton is not 1. The actual mass of a proton is super, super small. 1.674 times 10 to the negative 24th gram. It's super, 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 super tiny. So we'll talk about later that the relative atomic mass scale came about so that we wouldn't have to talk about the masses of these protons, neutrons, and electrons in terms of to the negative 24th power gram. The proton is located inside the nucleus. Its electrical charge is positive. And the importance of the proton is that it is the atomic number, which is the identity of the element. Every element has a unique number of protons. If you change the number of protons, you have turned it into a different element. It is sort of the DNA or the identifying social security number of the proton. And we learned earlier that it was discovered by Ernest Rutherford in 1909 with his gold foil experiment. The electron. The symbol for the electron is the E with the negative symbol. Again, very simple to remember. E stands for electron. Negative shows you the sign. Its relative atomic mass is 1/1836, a fraction, a very small fraction of an atomic mass unit. In other words, it is a lot smaller than a proton. Its actual mass is 9.11 times 10 to the negative 28th. Notice that for the proton, it was the negative 24th gram. The electron is even smaller with a power of negative 28 gram. It is located in the energy level outside the nucleus. Its electrical charge is negative. The importance, the electron is very, very important. The number of electrons located in the last energy level, they are given a special name called valence electrons, determines the chemical activity of the element. And it is from those valence electrons that we can predict chemical bonding and chemical activity. And it was discovered by J.J. Thomson in 1897 with his cathode ray experiment that we learned about earlier. The neutron. The neutron symbol is the N. Sometimes you will see a little neutral circle up there as well. Its relative mass is 1 atomic mass unit. Exactly the same as a proton. So a proton and neutron have the same mass. Its actual mass is 1.675 times 10 to the negative 24th. Again, very, very similar to the mass of a proton. Its location is inside the nucleus. Its electrical charge is neutral. The importance of the neutron is that it's responsible for isotopes, which are atoms of the same element with different numbers of neutrons. We'll talk about that later, but basically a neutron changes the mass of the atom. And it was discovered by James Chadwick in 1932. An element square on the periodic table provides us a lot of information about the protons, neutrons, and electrons. For example, lithium, its symbol is Li. The whole number that is written often to the top, either the top center or the top left, sometimes the top right, gives you the number of protons and electrons in a neutral atom. So the atomic number gives you two things, the protons and the electrons in a neutral atom. The decimal number on the bottom, usually 6.941 in this case, is the atomic mass, the relative atomic mass of the element. So 6.941 is the atomic mass. Over here, the 3 is showing you that there are 3 protons, 3 electrons, and then it also says 4 neutrons. How did I come up with that number 4? Well, if you remember, the nucleus is where the protons and neutrons are. The mass of an atom is all based on the mass of the nucleus because these electrons are so small, their mass is negligible. So the atomic mass of 6.941 is the mass of the protons and the neutrons. So if we round 6.941 up to its nearest whole number, which is 7, it tells us the mass of the nucleus is 7. Well, if we know that 3 of those 7 atomic mass units, or the mass from it, comes from the protons, it means the other 4, to add up to 7, are neutrons. So when rounded to a whole number, it is the total number of protons and neutrons added together. So even though the neutrons are not directly provided for you on an element square, it is calculated by taking the mass rounded to the nearest whole number and subtracting the atomic number. So in this case, 7 minus 3 gives you 4 neutrons. Fill in the table of protons, neutrons, and electrons. We will go through this in class. So you can pause and give yourself a couple minutes to go ahead and fill that in if you would like to do it now. And then I will just go through them here. You can check your answers. You can pause the video to check your answers. I will go through one of them with you. Let's do hydrogen. I don't have a periodic table right in front of me, so I don't know some of these masses off the top of my head, but I do know hydrogen's. So hydrogen's atomic number is 1. So that's why it has 1 proton and 1 electron. Its mass on the periodic table is 1.0 something, 811 maybe. So to get the neutrons, you would take that number, subtract 1, and that's where the 0 comes. Isotopes. An isotope is an atom of the same element that has a different mass due to having different number of neutrons. Remember that the mass of an atom are the number of protons and neutrons together. You can't change the protons without changing the identity of the element. So the only thing that can affect the mass of an atom are the number of neutrons. So an isotope has a different number of neutrons, same number of protons. The atomic mass on the periodic table is an average of the abundance of all the isotopes of that element. We will talk about how to calculate that later. So for example, these are 3 isotopes of hydrogen. We have hydrogen 1, hydrogen 2, and hydrogen 3. By the way, the 1, the 2, and the 3 give you the isotopic mass. So hydrogen 1 has a mass of 1, hydrogen 2 has a mass of 2, hydrogen 3 has a mass of 3. Now in hydrogen 1, you have 1 proton. In hydrogen 2, you also have 1 proton. And as expected, in hydrogen 3, you have 1 proton. So in hydrogen 1 then, how many neutrons would you have to have? 0. because this one contributes to that one solely. In hydrogen 2, you would have 1 neutron because you would add this one plus this one to give you the 2. In hydrogen 3, you have 1 proton, which means that you would have to have 2 neutrons to give you a mass of 3. The abundance on the bottom tells you the number of isotopes in nature that have that mass. So 99.985% tells you that in a sample of all hydrogen atoms, 99.985% of them will have 1 proton. 0.014% of hydrogen atoms have a mass of 2 AMUs, and 0.001% of hydrogen atoms would have a mass of 3. So the number on the periodic table is a relative weighted atomic average of those 3 isotopes. If they were equal amounts, if it was 33%, 33%, 33%, you could find an average simply by adding up 1, 2, and 3 and dividing by 3. However, their abundances are not equally distributed, and therefore there is a formula that we have to use, or that has been used, that finds the weighted average of those isotopes. And again, we'll talk about that a little bit later. Isotopes are atoms with the same number of protons but different number of neutrons. Atoms of the same element which have the same atomic number but different masses. There are several ways to represent an isotope. These are 2 isotopes of chlorine. So one way is to have the symbol here, and then these numbers are the isotopic masses. So chlorine 35 has a mass of 35, chlorine 37 has a mass of 37. The 17 is the atomic number. So notice that both of the bottom numbers stays the same because chlorine's set atomic number is 17. Another way to represent isotopes is in the hyphenated form. So that is the one that is in orange down there. You can write out the word chlorine with a hyphen, and then after it put the mass of that chlorine isotope at the end. Notice that here it's located in the corner, the upper left-hand corner. Here in the second format, it is located after the word. There's no need to write the 17 for the hyphenated version because if you have the word chlorine, it is assumed or understood that you can look at the periodic table and find chlorine's atomic number as 17. So let's take a look at these isotopes and see if you can fill in their protons, neutrons, electrons, and hyphenated name. Go ahead and press the video on pause and see if you can do this without my help. All right, for the first carbon isotope, its number of protons is 6. Its number of neutrons is 6. That is calculated from 12 minus 6, the mass minus the atomic number, and then the electrons is 6. And the name would be carbon-12. 12 comes from the mass. Carbon 13, 6 protons, 7 neutrons, 6 electrons. The name is carbon 13. Carbon 14, have 6 protons, 8 neutrons, 6 electrons, and then carbon-14. Let's go ahead and do it for the 3 isotopes of calcium. You can press pause and fill this in on your own. Number of protons for calcium-42 is 20. Number of neutrons, 22. The number of electrons, 20. And the name is calcium-42. For the next one, 20 protons, 23 neutrons, 20 electrons, and then calcium-43. 20 protons for the next one, 24 neutrons, 20 electrons, and calcium 44. All right, let's do one more. We'll do these quickly. Zinc, protons 30, neutrons 34, electrons 30. Name zinc 64. For the next isotope, 30 protons, 35 neutrons, 30 electrons, zinc 65. Oh, shoot. Sorry about that. Sometimes I press the wrong button and it takes me all the way to the end of the presentation. The third isotope, we have 30 protons, 36 neutrons, 30 electrons, and the name is zinc 66. Masses of atoms. So a scale was designed for atoms that gives their small atomic masses in units of atomic mass units that we talked about earlier. An atomic mass unit is not a gram. An atom of carbon-12 was assigned an exact mass of 12.00 AMUs. The relative masses of all other atoms was determined by comparing each to the mass of carbon-12. Since carbon was the most abundant element back in the day when they were designing the periodic table, they said, this carbon right here, we're going to say, has a mass of exactly 12. Everything else on the periodic table, all the other elements, are relative to that set starting point. So a mass of 24 AMUs means that that atom is twice as heavy as carbon. A mass of 6 AMUs tells you that that atom is half as heavy as carbon. And again, these are not actual masses. These are relative atomic masses that were designated so that we wouldn't have to work with really, really, really small masses, like 10 to the negative 24th grams. Okay, so the periodic table have relative masses that are shown. The relative atomic masses are listed on the periodic table. It gives the mass of an average atoms of each element compared to carbon-12. The average atom is based on all the isotopes and their abundance. The atomic mass is not a whole number. The way to calculate the average atomic mass, which is something that you're going to have to know how to do, is by calculating a weighted average mass of the mixture of the isotopes of that element. The way you find this is through the following formula. It is the sum of the mass of the isotope times its relative abundance. This sigma sign means that if there is more than one isotope, you would add the product of the second isotope and its abundance until all of the isotopes have been accounted for. So, calculating atomic mass, the percent abundance of the isotopes should be given to you. The mass of each isotope of that element should also be given to you as well. And the weighted average is calculated using that formula on the previous page. So you take the mass of isotope 1, multiply by its percentage. Add to it the product of the mass of isotope 2 and its percentage, and if there's more isotopes, you would do the same thing. The percent abundances have to be in decimal form. So in other words, if it says that your percent abundance is 39%, when you put it into that calculator or into that formula, you have to divide by 100 to make it 0.39. One time you want to be really careful with this is on the practice worksheet. You will see that there's like percentages that are like 0.023%. That means that when you put it in your calculator, even though it's a really small number already, you have to put it in even smaller terms by dividing by 100. So just be really sort of careful with that, because a lot of people see 0.023% and they'll put in the 0.023, and they do not account for the fact that you have to divide by 100 to get it into a decimal form. Let's take a look at how to calculate the average atomic mass of magnesium. So you have 3 isotopes of magnesium: magnesium 24, magnesium 25, and magnesium 26. So the masses are 24, 25, and 26. Their relative abundances are 78.7%, 10.13%, and 11.17%. So in order to calculate the weighted average, you are going to take the mass of the first isotope, which is 24, and you're going to multiply it by 0.7870. So that's the mass of isotope 1 times its abundance in decimal form. For the second isotope, you're going to take its mass, which is 25 AMUs, and you're going to multiply it by 0.1013%. So that's 25.1013. Then you're going to add the third isotope. So that should be 26 times 0.1117%. My recommendation is you find the products first and then add the 3 products together. You should get 24.3 AMUs, which should correspond to the number that appears on the periodic table. That is how those numbers are calculated, using these weighted atomic masses of the isotopes. Let's take a look at this one. Go back. It says gallium is a metallic element found in small lasers used in compact disc players. In a sample of gallium, there's a 60.2% of gallium-69 and 39.8% of gallium-71. What is the atomic mass of gallium? So here, you are given the isotope and its abundance, and you are given the same element, different isotopic mass, and its abundance. So the way you would calculate this is the following. You would take the mass of isotope 1 times its percentage, multiply it together, do the same thing for gallium-71 times its percent, and then simply add the 2 together, to get 69.7 AMUs. Let's take a look at this. Carbon 11, carbon 12, carbon 13, and carbon 14. And their abundances are down here. So for the first one, you would take 11 AMUs times 0.04%. So let me take that out and put 0.04%. I should have changed it to a decimal. For the second isotope, you're going to take 12 AMUs times, should put in 0.75%. The third isotope, 13 times 17%, and the fourth one, 14 times 0.04%. So when you multiply those together and then add them, you should get 12.01 AMUs. Let's do this one. We have boron 10 and boron 11. Boron 10 has an abundance of 80%. Boron 11 has an abundance of 20%. So here, to calculate the average atomic mass, you take the mass of the first isotope times its abundance in decimal form, plus the mass of the second isotope times its abundance in decimal form to give you 10.81 AMUs. If the numbers are slightly different than the periodic table, it's just a matter of rounding and sig figs that different books use, but as long as you are ballpark, then you should be good to go. Silver has 2 naturally occurring isotopes. Calculate the average atomic mass of silver giving the following data. So for isotope 1, you take its mass times its abundance in decimal form, plus the second mass times its abundance in decimal form to get 108 AMUs. Three isotopes of silicon. To calculate its average atomic mass, you take 28 times 0.9221 plus 29 times 0.0470 plus 30 times 0.0309 to get 28.3 AMUs. And we will stop there for today.